Hi Chem 240, it's Dr. Ricardo here. We're going to start the first video for chapter 19. It's thermodynamics and equilibrium. Probably be 4 videos. A couple of constants and a couple of things to remember about units. There's a new constant that you're going to see called the Boltzmann constant. We'll talk about it later on. It has mostly to do with entropy, so we'll talk about it in the second half of the chapter. It's 1.38 times 10 to the minus 23rd joules per Kelvin for each molecule. And it turns out that it's going to be directly related to the R value that we've been using, the energy R value. So whenever you're working in this chapter, chapter 19, and you need R, you're going to use 8.3 joules per mole Kelvin. The way you get from here to here is really interesting. This is the constant per molecule. This is the constant per mole. So if you take the Boltzmann constant and multiply it by Avogadro's number, you get this. You get 8.3 times 8.31 joules per mole Kelvin. Remember, the other R we use is liter atmosphere per mole Kelvin that we use when we do gas questions. So this is the energy R. Okay. In terms of pressure, in this chapter, if you need pressure, it's kind of a physicsy chapter, you need to put it in the SI unit of pressure, which is pascals. And pascals, if you want to convert them to atmospheres, it takes 1.031 times 10 to the 5th pascals to make an atmosphere. Another way to look at that is 101,325 pascals make an atmosphere. Okay, this one is just written in scientific notation and has one less significant digit, one less significant digit. Okay, what is a pascal? Pascal is a Newton per meter. That's the way it works into force per unit area, which is what pressure is. And anytime we're working in volume, instead of working in liters, we have to work in meters cubed, which is a huge unit. It takes 1,000 liters to make 1 meter cubed. Okay, we never do anything in the chemistry lab that's meters cubed. Okay, because you think about that, that would be, you know, a meter times a meter times a meter would be a huge box. It would weigh thousands of pounds. That's too large for us. Okay, but you just have to convert it to work in this chapter. Okay, so the first thing that we're going to work on is a little bit of a review from Chem 1, and that is talking about U, capital U, which is the internal energy, and then defining a new important unit of heat and energy called enthalpy. So let's start with the review of internal energy. So internal energy, you learn this in Chem 1. Capital U is the sum of the kinetic and potential energies of the particles making up the system. So when we talk about the potential energies in chemistry, we're pretty much talking about the potential to undergo a chemical reaction. Okay, so their chemical potential, how reactive they are. So a molecule like hydrogen would be considered to have a lot of potential energy. A molecule like oxygen has a lot of potential energy. Gasoline has a lot of potential energy. It has a high ability to react. TNT has a high potential energy. Things like water and carbon dioxide and dried concrete have very low potential energies. Plus the kinetic energy. Okay, so these two things on their own are very hard to measure for a molecule. Okay, so a better way to think about it is to watch the internal energy of the system. How much does it change? How much energy is added from the outside and how much is lost? So that we can think of as delta U. The change in the internal energy of the system is U final minus U initial. If you want to use 1s and 2s, it's U2 minus U1. Okay? Again, U is a state function, meaning it's independent of the path that you take to get there. If an example of this would, an analogy to this would be the altitude or the height of a mountain. Okay? Pikes Peak in Colorado is about 14,900 feet. Doesn't matter which trail you take to get to the top, it's 14,900 feet above sea level. Doesn't matter the path that you take. Temperature is another example of that. If I tell you the temperature is 50 degrees Celsius, doesn't matter how you got there. You could have gotten there from going high, you could have gotten there from it being lower. It's what it is at the moment. Okay, other things that we're going to work with are not state functions. They do very much depend on the path on which you took to get there. Okay, so let's look at the definition of a state function. and then we'll talk about some other things that aren't. So state function is a property of a system that depends only on its present state. It's independent of the path in which the system took to get to this present state. And what's important for you is U is a function of P, T, and N, the pressure, the temperature in Kelvin, and the number of moles. Those three values will give you the internal energy of a particular chemical system. Okay. Another example of something that's a state function is mass, right? The mass is a function of how many molecules you have. It's independent how you got there. Doesn't matter. Volume is also a state function, and what the volume is right now at that temperature. But here's one that isn't. So actually, I shouldn't have wrote this capital. I should have made this a small u, more like this kind of u, right? Because work is not going to be a state function. Work is the energy exchange that results when a force moves an object through a distance. So this is work as it's defined in physics. Whenever we do work is done on the system, okay, so I push in on the system and I apply a force to it so that it has that energy stored up for later on, kind of like compressing a spring would be a great example, right? It's a force times the distance. That's how much work it would take to compress the spring. So work, if anytime W comes out to be positive, that's work done on the system by the surroundings. So I have a spring, I push in on it, okay? Push in on the spring, I compress it, that would be work being positive. When I release the spring, I take my hands off of the spring and it bounces out, that's work being done by the system on the surroundings, okay? So W would be negative. That's work done by the system on the surroundings. Okay, so W, work, okay, and work is gonna be important, right? We can use, I'll give you a great example. Internal combustion engine uses chemical reactions to deliver heat and pressure, and that heat and pressure is primarily used to do work on the pistons, push them down so you drive down the road. The waste products and the of carbon dioxide, water, and the extra heat that can't be harnessed to drive down the road are really lost and aren't the thing that we're of interest in. We're interested in the 30% of the energy that the internal combustion can provide to the car to drive you down the road. The other 70% is lost in all sorts of different ways. Okay, so we have a small w, okay, even though it's not small here, which is going to be the work. And the other thing is we're going to have the heat. And we know about heat. Heat is small q. It's the energy that flows into or out of a system. Heat, then, can only be transferred from one object to another if the two objects are at different temperatures. And heat always moves from the warmer object to the colder object. You can't move coldness, right? Your refrigerator functions not by making coldness and pushing that coldness into the freezer or the refrigerator. It works by extracting the heat out of that space in the refrigerator or the freezer and rejecting it and pushing that heat out into your kitchen. That's why the bottom of the refrigerator is usually warm. Okay, no such thing as coldness. The way things get cold is you remove heat from them. Okay, well, this is something that we are familiar with. Q, whenever it's positive, that's endothermic. Heat is gained by the system. We consider that uphill, right? That would be a good thing for heat to be gained by a system. So I have a heat exchanger, and the system that I'm interested in is at a lower temperature. It's in contact with something that's at a higher temperature, and the heat essentially will be leak out of the hot object into the cold object to warm up the cooler object. If you're the cooler object and you're the system, then that would be an endothermic process. An exothermic process would be if the system was at a higher temperature than the surroundings and it leaked heat out into the surroundings. That would be heat lost by the system. Exothermic, downhill, and Q is equal to negative. Okay, so the first law of thermodynamics, again, which you learned in General Chem 1, is putting these two ideas of Q and W together. So first law of thermodynamics says the change in the internal energy of our system, delta U, is equal to Q plus W. So the internal energy will go up, the system will be happy, it will gain energy, it'll have more internal energy if the sum of the Q and the W turns out to be positive. So maybe Q is very positive and W is a little bit negative. Maybe it loses a little bit of work. As long as this guy beats this guy out and the total sum of it comes out to be positive, that would be an endothermic process. Okay? All right. The heat of a reaction and internal energy. So let's break up what work is into something that's a little bit more practical for a chemical system, and that is a piston. So I can look at this formula here, which says the work done by the system. Okay, so work done by the system is equal to the force times the distance. Okay, well, if it's work done by the system that I want to start my definition as, right, that's my starting point, and I need to slap a W in front of the work, because if work done by the system is going to, the system is going to lose energy. That's where that negative comes from, because it's done by the system. Okay, work is defined in physics as a force times a distance. So you have a force and you push in on something for a certain distance. I want to push a box across a plane. What force is needed to get it moving multiplied by how far it moves. Okay? Well, we can break up distance into an interesting way of viewing distance. If I have a piston, so let me draw a piston for you on a different piece of paper. Okay? If I have a piston with a constant face area, so let me have my piston, let me see which way it would make the most sense to draw it. I'm going to draw it up, okay, just like you would think of a car. So here's my cylinder, okay, this is a chamber. This is solid material here, okay, good insulator, hold everything in. Well, what do? I have a tightly fitting cylinder, that piston, that fits in, and there's an O-ring around the outside. So this guy from the top view is circular, but when I'm looking on it face on, I just see the face of it. So think of this like a hockey puck moving up and down inside of a cylinder. Okay. Well, it has a rocker, an arm to it, okay, that connects to different parts of your engine. So whenever this guy is moving up, right, I'm compressing the gas that's in there, which is the system. And what's going to happen is that the area of the piston is going to be constant. That doesn't change. The only thing that changes is this distance that I move up and down. And when I move the hockey puck or the piston up and down inside of that space, doesn't the volume inside of the space also go down? So this guy moves, and also the change in volume is also going to change up and down when the piston goes up and down. Okay? So up, right? What's going to happen is if I'm going up and I'm doing work on the system, delta V is going to be negative, right? Because the space inside the piston, if it's compressing, is going to get smaller. Okay? If I'm going down, draw another piston. If anytime I'm going down, that's when the engine provides the work. So if the piston is in there nicely, tightly fitting, right, so that no gas can go around the outside, whenever I'm going down, then what's happening to delta V? Delta V is going to get larger, okay? This guy is work done by the system, right? If this guy's work done by the system, that's not good. That's W is equal to a negative, right? So whenever delta V is positive, W is going to be equal to negative. Over here, when I'm doing the compression, delta V is negative, right? That's work done, so we get W is equal to a positive. This is work done on the system. So what's going to happen is the negative sign in the formula on delta V is going to cancel out with our negative sign here, and we'll be able to get the pressure will always come out, the volume over here, the volume change can be positive or negative, but the pressure will always be positive. You can't have a negative pressure, okay? All right, so those are the two different versions. All right, let me show you the formula now. So see if this makes sense. I'm going to substitute in for D, right, my change in volume should be equal to the change in what is volume? The length times the width times the height of this cylinder. Well, this cylinder is a circle, so it has an area, and the only thing that's changing is the height. The length and the width are staying the same. The cylinder has a certain diameter, it's moving up and down. It's not going to change, okay? I'm pretending that this is a square. This would be the area of a circle times the height to do my cylinder. But mostly, this guy isn't going to change, right? So I can pull that out. That doesn't change. That's going to be equal to the area of the cylinder, right? The area of the cylinder multiplied by how much its height changes, right? Because that's the only guy that gets to change. That's D, right? The distance that it moves up and down, okay? So height is D. All right, so this, guys, is, this guy is delta V. So if I want to solve this for distance, I get distance is equal to delta V divided by the area, okay? So that's where that came from. Delta V divided by the area came from that analysis, that when a piston moves up and down inside of a cylinder, the area doesn't change. The only thing that changes is the height of the piston, and that's what causes the volume change. Again, picture this piston going up, area of this not changing, the height is changing, and the volume is changing because the height is changing. The amount of volume of gas trapped inside here is going to be different. When it's squeezed in, it's going to be lower than when it's pulled out, like in this case down here. Okay. All right, so I plug in D is equal to delta V over A in for D, right? Here, I plug that in. And then what do? It's algebra, right? So I just move this A under here, so I notice something. And I notice, hey, I know the name of force divided by area, right? This times this divided by this, I can just group these guys together. And force over area, guys, is pressure, okay? So if the pressure isn't changing, the thing that's changing is the volume, then you can pull this out, okay? And W is equal to minus, right? Look, where did this minus come from? I just cross multiply, bring the minus over to this side. It's equal to minus P times delta V. So that's a formula that you really should start to hold close to your heart. In our chemical systems, W is equal to minus P times delta V. Okay, I'll show you what that means. That's really important. It means that whenever something expands, right? It expands, it's delta V. Think about a piece of rubber. Whenever a piece of rubber, when it warms up, expands. Well, it did work on the world because when it expands, delta V is larger. If I multiply that by the pressure, so I'm letting the volume change, not letting pressure build up, multiply that by the pressure, it will give me a minus sign and W would be negative. That makes sense because that was work done on the system. How about the winter times comes and the rubber in between the cracks in the cement contracts, right? Everything contracts a little bit in the wintertime. Well, if that rubber contracts, then delta V is a smaller number, right? The volume goes down. So this guy comes out to be negative. Pressure is always positive. Negative times a negative equals a positive. That would be work done on the system. Anytime something contracts, you're going to get W positive, work done on the system. That's good for the system. It holds energy in the form of W. Anytime something expands, delta V is going to be, expand is going to be positive. So then if this times this is positive with a negative in front, W will be negative. That's whenever work is done by the system. So expansion, W negative, contraction, W positive. Go back to how our car runs. Okay, where's my pistons? Gotta be someplace. Okay, all right. Which is the stroke that creates the energy? The down, when the engine, the explosion pushes down, that's called a power stroke. Pushes down on the piston, that gas, that trapped gas, that's explosive mixture is losing work, right? It's doing work on the piston to push it down. So the chemical system's energy goes down, and the piston captures that energy and transfers it to the wheels in your car. Okay? So delta V positive is an expansion of the system. W will always be negative. Delta V negative is a contraction of the system. W will always be positive. We are only going to, now in the real world, the pressure is also building up inside a piston, right? So it's a little bit more complicated. You'd have to do calculus. What we're going to do is we're going to study only constant pressure systems. So anytime a chemical reaction occurs that forces are pushing out, we allow the chamber to expand because it's done inside a piston. So the space expands, so all of the work goes to a change in volume and not to changing the pressure. So if an explosion occurs in the piston, we're saying that it occurs in such a way that the pressure remains constant and the volume would get bigger. Okay? Again, a lot of times for us, P is going to be constant. In fact, the next term that we're going to come up with is particularly for that, for constant P. This is really important in this chapter, right? The work done at constant pressure is going to have a name. Okay, this guy's coming over here. So, sum it up. Delta U is Q plus W, first law of thermodynamics. At constant pressure, in our kinds of systems, in chemical systems, we substitute in what W is, and W is equal to minus P times delta V, right? So this is the heat done at constant P. That's what that little P means, okay? And we have the first law, particularly at constant pressure. So since none of that pressure is allowed to build up, the pressure stays constant, okay, during the explosion, and the volume changes. The volume is going to get a lot bigger. Then that's going to be delta U. So delta U is now, at constant pressure, delta U is Q at constant pressure minus P times delta V. Why the minus sign? That came from what we just defined W as, right? W was minus P delta V. Before, right, we're substituting in here what work is, and work is equal to minus P delta V, so this whole thing substitutes in here. That's why you get the negative sign. Okay, so we're going to define a new parameter, and this new parameter is going to hold in place any changes in volume that are done at constant pressure. It's going to kind of absorb them into the heat term. It's much more useful than delta U, because delta U, you would always have to be taking into account how much things expanded when they got hotter and how much things contracted when they get colder. Well, if you define a new term called enthalpy, which is a state function, just like U, right? Independent of how you got there. H, we're going to define as U plus PV, okay? So if we take that, this is a definition. I'm just handing this to you right now. Don't try to find how I got it from up above. This is new. That's why I put 3 arrows. So H is a new state function that has built out of 2 other state functions, volume and pressure, okay? They're also independent of how you got there. So notice I got the W out, which wasn't independent. So I'm saying U is now U plus PV is H. Well, anytime I have H, I can also talk about the change in H. So the change in H is H final minus H initial, or if you like ones and twos better, H2 minus H1. Okay? So I could always do that. So what would happen if I take my new definition of U plus PV and I substitute it in here once for H final and once for H initial? That's all I did here is take this, substitute it in here, and substitute it in here. So in order to do that, I just have to make sure I keep track of my F's and my I's, right? So if I do it for H final first, I get U final plus P V final. Remember, P isn't changing, okay? It's at constant pressure. So enthalpy is a state function. So now everything down from here is going to be at constant pressure. So if P isn't changing, I don't have to say it's going to be the same in both cases. P is P. This is not a different number than that. Okay, that P is not a different number than that. And that's good because I'm going to be able to factor it out. So again, all I did was take this, plug this in here, put little F's on everything, plug that whole thing again in here, and put little I's on everything. Don't have to bother to put I's and F's here because they're the same. It's at constant pressure. So look what I can do then. I can group these two. What is U final minus U initial? Delta U. The change in U final minus U initial is delta U. Factor out the P and I get F final minus, V final minus V initial. What's that? That's delta V. Okay, so now I have a new term that says delta H is delta U plus P delta V. All right, well, what do we know? We also know from the first law of thermodynamics at constant pressure that delta U is Q at constant pressure minus P delta V. Let me show you that. That's just back a teeny bit. Oh, top of the page, there it is. So look how cool this is. I'm going to take my first law of thermodynamics at constant pressure and I am going to plug it in there. I'm going to plug that in there. And if I do that, that's those first two terms. These two things are exactly what you see over here. This is just me rewriting this. Oops, sorry. Okay. So here I'm going to plug this in here. So this and this are these two terms. These two terms. This is just the same thing that I had from over there. Now look what I get. I get at constant pressure, delta H is Q at constant pressure minus P delta V plus P delta V. So this thing from the definition of enthalpy cancels with the minus P delta V that comes from what the internal energy is. And I get this great concept, and that is that delta H, the change in enthalpy of a system, can be measured very simply. All you got to do is don't let the pressure change. As long as you do chemical reactions at constant pressure and you let the volumes adjust, not the pressures, only the volume is allowed to adjust, then measuring the heat of the reaction is equal to measuring the change in enthalpy. So the change in enthalpy is equal to Q at constant P. Okay? This is obviously true as long as the pressure is constant. Okay? So even though in real life, right, the pressure is changing all the time inside of our engine, we're going to do all our calculations as though the delta V is doing all the changing and the pressure is not changing. Okay? So you can list all of your thermodynamic properties in this special case, right, where we have constant pressure reactions, and you can calculate many other thermodynamic quantities that you're interested in by setting it up that you think about everything in terms of enthalpy. So again, what is enthalpy? Or what is the change in enthalpy? The change in enthalpy is the change in, is the heat of the reaction when the reaction is done at constant pressure. Okay, now, delta H then can be tabulated and put into textbooks that you can use. And you can calculate what the enthalpy is for any kind of chemical reaction. And you learn this from Chem 1. You can calculate it for any kind of chemical reaction based on a certain type of delta H's that are tabulated for us, okay? So delta H is the heat of the reaction when it is conducted at constant pressure. And if you remember from Chem 1, delta H for any reaction that you happen to be interested, right? Whatever the one that you're interested in, you wouldn't want to have a book that had every single chemical reaction under the sun. Their book would be huge. So the better way to do it is to tabulate them in terms of what would delta H be is if I looked at it in terms of delta H0 of formation reactions. So this again, this is, we know delta H is a state function, right? Because H is a state function. So it doesn't matter how you got there. So you can calculate it based on how much energy it takes to well, let's get the definition of what F means, right? So this is not final or initial. This is for formation. Again, formation reactions are how much energy it takes to make a particular chemical compound from its elements in their standard state. Okay, so however you would ordinarily find those elements, for instance, if you want to make carbon dioxide gas, you need to make carbon dioxide from carbon graphite, because that's the way you would find carbon in its natural state. Okay, carbon is not naturally in the diamond form, it's in the graphite form, right? And oxygen, you would have to make it as you would ordinarily find oxygen, which is O2 gas. So at normal temperatures, at 25 degrees, making the delta H of formation for carbon dioxide would be making carbon dioxide from carbon graphite and oxygen. Okay, so that's the way you do it. These numbers are tabulated. Some of those reactions actually are almost impossible to do kinetically. You would put those two things together and they wouldn't work. We wouldn't make them. But after a whole bunch of other chemical reactions were figured out, you could go back and put the puzzle pieces together and figure out what it would be to do the formation reactions. Okay, so this again, review from Chem 1, delta H for any reaction is the sum. Take into consideration all of the coefficients, okay, of the products minus the sum with the coefficients taken into consideration of the reactants. So best way to do this, practice from Chem 1, would be for me to pick one and do it with you. Okay, so I have an example of one that I want to do, and it's kind of cool because it's related to something that we've been working on in the last chapter, and that is acids and bases. Okay. So here's our example of calculating delta H for a particular chemical reaction, okay, using the delta H0 of formation tables. Okay, so I looked these two up for you already, or these three up for you already, and that is, this is in Appendix C of your textbook. It's on page 1090, and if you look them up, you want to make sure that you look up everything exactly the way you see it. Okay, so the states are important. Ice has a slightly different number, takes a little bit different amount of energy, a little bit less energy to make ice from hydrogen and oxygen than it takes to make liquid water. Water vapor would have a different number, so make sure you grab the right one, right? So you need this one, and this one. Okay, so let's talk about the reaction we're interested in. I want to know, right, for a neutralization reaction, the reaction of taking a strong acid and a strong base, right? So this could be HCl and NaOH, where the Cl and the OH don't contribute anything to the energy because they, as soon as you put them into water, create this species and this species. In a minute, I'll show you that this is the same as H3O+, okay? But in your textbook, they only give H+, so that's the way I wrote it in this simple form, okay? So delta H for the chemical reaction I'm interested in. So delta H for this reaction, okay? Did you see that? Good. Delta H for this reaction should be equal to the sum of the delta H of formation for all of the products minus the sum of the delta H of formation for all of the reactants. Okay? Last thing I have to consider is if there's any coefficients other than 1, I would multiply by those coefficients. So for instance, if there was a 2 here, the first number that I'm going to dig off the table is the delta H of formation of water, liquid. I would have to multiply it by 2, but there isn't a 2 here, okay? So I don't have to do that. So I go down here, I find water, it's equal to minus 285.8 kilojoules per mole, which is always going to be our units whenever we have enthalpy, okay? Same as it would be for energy, and same as it would be for internal energy. They have kilojoules per mole, okay? So minus 285, I take the products. Make sure you don't keep that sign on there. 285.8. That's the only product, so that's the only thing I need over there. And I need to subtract off all of the reactants. Okay, hydroxide in that table is negative 230.8. That means the amount of energy you get when you make hydroxide from water is from oxygen gas and hydrogen gas. When those two things got together to make hydroxide, it would be exothermic, right? Making it from its elements. This one, what is that number? How much energy gets released when you make water from hydrogen and oxygen? Again, that one happens to be exothermic too. Okay, so this guy goes here, so product minus the two reactants. This one is negative 230. Negative minus a negative. Okay, take care of that in a second. All right, plus the other reactant. Now this is really cool. The hydrogen ion is a special ion, right? It's defined, it's set equal to 0, okay? So the hydrogen ions, and this you'll see, it comes out in the thermochemistry and the electrochemistry later on in the next chapter, that the hydrogen ion is set with a standard potential of 0. That makes it the amount of energy to generate hydrogen ions from hydrogen in the gas state is 0, okay? So I need my 0 there. Okay, it's right on the table. There's a big fat 0 if you look it up in the book. Okay, so minus a minus is equal to a plus, 230. So really all I have to do is take my negative 285.8 and take off 230, right? So that's going to give me, looks like 55.8 with a negative sign, right? I'll double check it. Kilojoules per mole. So that's how you do those, okay? And you should have remembered that from, sorry, my screen went off, guys. See if I'm back. Good, okay. I don't think there's any interruption for you when my screen goes out. Okay. Let me just double check that. Right, 8 minus 3 is 5, that's good. Okay, so exothermic. We don't know how much of it came, obviously most of it came from the heat being released, but if there was any change in pressure, it's factored into that. It's already in there. This is how much energy would be released if you took 1 mole of hydrogen ions and 1 mole of hydroxide ions and let them react at room temperature to create water where there's no change in pressure, where the pressure does not change. This guy over here wouldn't create a lot of pressure change anyway. Okay, if it got hot, the volume would have to change. The water would have to expand a little bit. And it probably does a teeny bit. Okay, most of this is the change in heat. It gives up heat, not change in volume. Okay, but again, delta H, this is the same thing as Q if it was done at constant P. Okay, can't say that for internal energy. Okay, that's why we don't use internal energy as much in chemistry. We use enthalpy because we're allowed to, it's the heat of the reaction when the reaction is done at constant pressure. Okay, so one more thing I promised you is I wanted to show you that this would be exactly the same thing as if I did the way we tended to view things in Chem 2, was not as hydrogen ion, but as the hydronium ion. So let me show you a cool one. Let's do this reaction. What would happen if I asked the question, what is delta H for the reaction of the hydronium ion breaking apart to give the hydrogen ion and H2O? Liquid. Okay. Oh, excuse me, liquid. Well, this, right, is just this. We've always said those two things are equal, plus a water molecule. So I'm substituting what it is. And look, I got the same exact things on the left as I have on the right. So I would look up this number, add it to this number, which we know this one is 0. This one we just had, 285, right? So I'd get 0 plus a negative 285 for my product side. And look, I got the same exact thing on the reactant side. So they're going to be tied. So it's just another way of thinking about it. But we know these two things, right, can be thought of equivalently as chemistry. Now, if I was going to do delta H, I would take the products minus the reactants. These are the products. They sum up to negative 285. If I subtract off the reactants, negative 285 minus a minus negative 285 gives you a big fat 0. I didn't do any chemistry. This is exactly the same all the way across. Okay, so that's it for this first video for the thermodynamics chapter, which is chapter 19. Okay, thank you guys. We'll see you soon.